Hello, everyone. Today we are going to talk about Anova. So for Anova, we're going to use what is called the F distribution. So there is a different F distribution for each different pair of degrees of freedom for numerator and denominator. The F distribution is not symmetric. It is skewed right. Values of the F distribution cannot be negative. The exact shape of the F distribution depends on the two different degrees of freedom. So the nice thing here is it's not for a normal distribution. So if we don't have a normal distribution, we might have to use an F distribution. And below, this is a sample of what it might look like. It's not symmetric, it's skewed to the right. It has non-negative values only, so it always will be greater than 0. And then here's a potential critical region where it is skewed to the right. This whole tail is our critical region. So let's define it now. One way analysis of variance, which we call ANOVA, is a method of testing the equality of 3 or more population means by analyzing sample variances. So one way analysis of variance is used with data categorized within one factor. So there's one characteristic used to separate the sample data into different categories. So let's look at the key elements for ANOVA. So the objective is to use samples from 3 or more different populations to test a claim that the populations all have the same mean. So requirements are tougher here. The population has distributions that are approximately normal. This is a loose requirement because this method works well unless a population has a distribution that is very far from normal. So most of the time it'll work even if it's not normal. If it somewhat looks like normal, that's okay. The populations have the same variance squared or standard deviation. Again, this is a loose requirement because this method works well with the population variances that differ by large amounts. So it can vary by a large amount. And then the more important ones here are the samples are simple random samples of quantitative data. Samples are independent of each other, and the different sample sizes are from populations that are categorized in only one way. So 3, 4, and 5 are what really matter. 1 and 2 are nice, probably give you a little bit more accurate data, but it's not the end of the world if it's not perfectly normal or the variances aren't perfectly the same. So the procedure for this test is we're going to use technology to obtain results that include the test statistic and p-value. We want to identify the p-value from the display. The ANOVA test is right-tailed because only large values of the test statistic cause us to reject the quality of the population means. And 3, we're going to form a conclusion based on these criteria that use the significance level alpha. We reject if the p-value is less than or equal to alpha, fail to reject if the p-value is greater than alpha. So our null hypothesis here is that all of our means are equal. It could be 3 means, it could be 4 means, it could be 5 means, just more than 2. Right. So little notes here, because the calculation required for one-way analysis of variance, or ANOVA, are messy, we're only going to do this method using technology. We're never going to compute this by hand. And we want to understand that a small p-value leads to rejection of the null hypothesis or equal mean. With a large p-value, we fail to reject the null hypothesis of equal means. Let's look at an example. So we have size of vehicle and head injury measurements. So we're going to use the head injury criteria measurements listed in the table and use a significance level of 0.05 to test the claim that 4 samples come from population with means that are all equal. So in our requirements, we talked about how they have to be separated by just that one factor. Here it's the size of the car, small, mid-size, large, and SUV. That's that one factor that we're breaking up our samples into. So let's do our requirement checks. Based on the 4 samples listed, the 4 populations appear to have distributions that are approximately normal. I'll give you that. The 4 samples in the table have standard deviations that do not differ by considerable amounts, so the variance is about the same. So both those aren't super important, but they are true in this case, so that's nice. We can assume the samples are random because there's no information given for us to assume otherwise. The samples are independent of each other. You can't be a small and mid-sized car. You're just small or mid-sized. The categories are separated by a single factor being size of the car. So we're good. We can do Anova. So let's look at this solution. So our null hypothesis will always be however many samples we have. In this case, we have 4. We're saying that all 4 means are equal. Our alternate hypothesis is going to be at least one of the means is different from the others. All of the means could be different, but all it needs is to have one mean different from the others. And our significance level is going to be 0.05. Okay. So let's look at the SPSS version of this. So we have our degrees of freedom. We don't really care about sums of squares, mean squares. What we're looking for is this F value. F is 7.685. So that will be on our distribution, that large value. Let's see what this means. So in addition to the test statistic of F equals 7.6853, the display also shows the p-value is 0.00 when rounded. So the significance is our p-value here, 0.000, which doesn't look like much because it's nothing. It rounds to 0. Okay. So we can either use this value or we could use this value. When the p-value is less than 0.05, oops, we have an extra 0 in there. It's less than 0.05, even though this one is less than 0.005. When it's less than 0.05, the significance level, we reject the null hypothesis of equal means. So p-value is less than critical value. So we're going to reject the null. There is sufficient evidence to warrant the rejection of the claim that the 4 samples come from populations with means that are all equals. So since we reject the null, that tells us there is sufficient evidence that warrants the rejection of the claim. And this all goes back to our chart still of how we use summaries when we reject the null. That gives us sufficient evidence to warrant the rejection of the claim that the 4 samples come from the population with means that are all equal. Which makes total sense if you think about what this question was asking. If we have crash tests of small cars, makes sense that we have higher injury measurements. Just think about that in practicality. Small cars get into car crash, you have less protection. Big car probably has less of an injury. So it makes sense that we don't have the same mean for all the types of cars. So that's just what it appears like common sense wise, but that's not a proven fact. It makes sense that we can warrant the rejection of the claim here. All right. So just be careful when we conclude that there is sufficient evidence to reject the claim of equal population means. We cannot conclude that any particular mean is different from the others. There are several other methods that we can use to identify the specific means that are different, and some of them are discussed later in the units. But for now, this is all we're going to take a look at. So just because there's sufficient evidence to reject the claim, that's all we know. We don't know if it's mu2's fault. We don't know if it's mu3's fault. We know we can't say they're all equal. That is all that this tells us. We cannot say all 4 means are approximately equal. All right. That's going to be it for all of the lessons. Have a great day, everyone.